is a short presentation on Fermi level fluctuation, magnetization and Zeeman splitting during quantum oscillation in nodal line semimetals by Anupam Saha. The work is going on under the supervision of Dr. Satyaki Kaur from AKPC Mahavidyalay, India. These are the content of my talk. According to band theory, the gap between conduction band and valence band classified the materials as metal, insulator and semiconductor. In semimetal, for some of the discrete wave vector in Brillouin zone, there is a gapless spectra. So at those k values, the gap between conduction band and valence band is 0, but it is non-zero for other k values. It makes interesting when the crossing is linear, then things changes dramatically, because in linear crossing we have effective mass to be 0 at the crossing point, and it gives huge mobility to the particle. To working with linear crossing, we have to use relativistic Dirac equation rather than Schrodinger equation. Here a continuum model that resembles a massless Dirac Hamiltonian. Typically for graphene, it produces the so-called Dirac points where conduction band and valence band touch, the dispersion being linear at that point. In 3 dimension, we have the massless Dirac equation. Thus, while fermions propagate parallel or anti-parallel to their spin, which defines their chirality, those are the Weil semimetal. In Weil and Dirac semimetals, conduction band and valence band touches at point in 3 dimension Brillouin zone. If the band touching occur along lines, those states are termed as nodal line semimetal. Many experiments have been done on nodal line semimetal, and some compounds are ZrSiS, Ti, TaSe2, etc. These nodal rings or loops appear when symmetry constraints allow band crossing with linear dispersion and along lines in the Brillouin zone. We cannot make the nodal ring vanish by some deformation. Only ring can be small or big, that is the topological robustness it have. We can calculate the Berry connection, Berry curvature and Berry phase given by those equation and make a electronic path on putting different sides of nodal ring. We can say it is non-trivial or topological or non-topological by calculating Berry phase equal to 0 or not equal to 0. Again, by calculating Chern number, it can be say about local order or non-local order parameter. If those system, if we do quantum oscillation measurement, and from this one can easily calculate the Berry phase. On the basis of semi-classical treatment, electron in presence of magnetic field undergoes cyclotron motion. When we go into a momentum space, then Landau quantization come to the picture. All the required mathematical expression are given in the slide. We are look upon what happened physically. In absence of magnetic field, the electron states are uniformly spaced in k space, with each point separated by 2 pi by L, and those states coalesces and will rearrange from the original square grids into Landau levels in the form of circles for n equal to 0, 1, 2 and so on. As shown in figure, quantum oscillation can be described using famous Onsager relation, and we can say the level density will have a sharp peak whenever energy is equal to the energy of an extremal orbit, satisfying the quantization condition. Here a Landau tube, and for some energy height kz, the energy is Ekz. In the second picture, there is no orbits in the range E and E plus dE energy shell that occupy extremal position. Same construction have done in the third picture, except that here energy is now of extremal orbit, and for that we get a peak in density of a state plot. Here the figure shows a typical density of state plot for a fixed magnetic field, their change in energy for different Landau tube, we get this situation and it falls like one dimension density of state. Here it is our theoretical model. Let us consider a simple nodal line semimetal Hamiltonian with time reversal and space inversion symmetries. Here sigma denotes Pauli matrix for spin degrees of freedom. By diagonalizing, one can have the energy expression. If there is no gap, then we have the locus for px square plus py square equal to 2m0 m star, which is a circle in the px-py plane. So this is the nodal ring. So we can see the Hamiltonian describe a nodal line semimetal system. Now when in the presence of magnetic field, we use parallel substitution and putting the vector potential, we have the Landau quantization in energy form. Here those figure shows Fermi surface for the Hamiltonian. Include the Zeeman term, which is a number half g mu b into our previous nodal line semimetal system Hamiltonian. After doing all the similar mathematical calculation, we get those expression. Here tau and sigma are Pauli matrices for orbital and spin degrees of freedom. A typical Fermi surface in presence of Zeeman term is shown in the figure. Here we shows how the Fermi level fluctuate with the magnetic field variation in our nodal line semimetal. The Landau tube gets change their cross sectional area as the magnetic field is varied. Thus they successively cross the Fermi surface. For this time being, we put Zeeman term in a side and calculate the total number of particle or electron. After that, successfully write the chemical potential expression. This figure shows quantum oscillation dominates at large magnetic field values. After that, a constant periodicity occurs when plotted against inverse of field strength. Here, stick on thermodynamical approach at zero temperature analysis. We have calculated magnetization expression with include Zeeman term and plot it with inverse of magnetic field strength for different chemical potential values. As shown in the figure, it shows the quantum oscillation in magnetization. Those amplitude take small values when the field is tuned at low values. From the dispersion relation, we find out that the Zeeman splitting appears to be large for effective mass nearly equal to electronic mass for n equal to 0 mode, but for very small effective mass, Zeeman contribution becomes minimal for higher Landau indices. Again, for pz not equal to 0, the Zeeman term becomes less important as the lower cutoff energy m0 magnitude becomes non-zero as well. One can also see such behavior from field dependence of the Landau level spectra as shown in the bottom figure, where the smallness of Zeeman term is clearly seen for the small effective mass and Z equal to 38. The density of state varies with or without Zeeman term is shown here. We are obtain density of state from the basic definitions. One can notice that the peak in density of states almost retains their peak position as the Zeeman term tuned for the ratio effective mass and electronic mass, that is MR here, is equal to unity, but it becomes differentiable for smaller the ratio as shown in the figure. In summary, I would like to say that nodal line semimetal with field perpendicular to nodal plane does not report any topological oscillation. So we plan to study the scenario where field acts in the nodal plane to study the topological magnetic oscillation occurring there. Our research work is supported by DST SERB Government of India. Thank you all for your kind attention.